So working scientifically on here, looking at infrared radiation. So a student investigates how much infrared radiation is absorbed by different surfaces. And the photograph shows some of the equipment available to the student. So the student pours some water into each bottle. Describe a method the student could use to investigate how the colour of the bottle affects the amount of infrared radiation. So we can draw a diagram if we want to. This is where I refer you to EMMAs. Okay, so EMMAs, equipment, method, measurements, analysis, safety. So whenever tackling practical 6 markers, use this. So the equipment has already been done for us. So if we go on to our measurements and our method, we can kind of do those together. Our measurements are all about our variables. Now we've been told what our independent variable is. It is the colour of the bottle. And we've been told what our dependent variable is, that is the amount of radiation absorbed. But these 6 marks are awarded because you are asked to try and describe a method that will lead to a valid outcome. So to have a valid outcome, we need to have control variables. So when describing your method, okay, we know we've poured some water into the bottles, but what do we do with those bottles then? So the first thing to identify here is that if they've got water in them, a control variable here must be the same amount of water in each bottle. Now, what we're trying to identify here is when they are placed close to the heater, how much radiation are they going to absorb? So in order to do that, we need to put them near the heater. But again, thinking about control variables, we have to make sure that that is an equal distance. So the next thing we need to talk about is placing those 2 bottles an equal distance from the heater. Now, our heater, it's really important if we want to know how much radiation they've absorbed, we have to ensure that they're both receiving the same amount. And we've partly dealt with that by addressing the distance that we are from the heater, but we need to get the idea of the same heater setting or the same heater output for both bottles. Now, in order to identify how much radiation they've absorbed, we can see from our equipment that we are looking at a temperature rise here. So in order to do that, because the temperature of a substance in relation to its surroundings affects how quickly it will heat up and cool down, we have to make sure that the starting temperature of the water in both bottles is the same. So there are our measurements, the things that we need to make sure we are keeping the same as part of our method. So having placed the bottles there and put in various control measures to make sure that it is going to be a valid set of results, what are we then going to do? Well, we need to turn the heater on and we need to leave them for a set period of time. And after that set period of time, we want to know how much the temperature has risen by. So what we're then going to do is record the temperature after a set time. Now you could give a time there, you could say 10 minutes, 5 minutes, doesn't really matter. But the idea is that we know that we're leaving it there for a certain amount of time to allow it to heat up. So that now takes care of our measurements and our methods. The last thing as part of the method, in order to make sure this is valid, we need to have a repeat of that investigation. Okay, then we come on to our analysis. So having done this, having taken the temperature change as we've heated these different bottles up and we've repeated it, what do we then do with that? Well, we actually then calculate a mean temperature rise. And you may include in there omitting any anomalies. So then we come on to S, our final part, which is our safety. And when dealing with safety, we always talk about 3 things. So the first thing is, what is the thing that is going to cause a potential problem? The second thing is, what is the potential problem it's going to cause? And the third thing is, well, how do you stop that from happening? Okay, so whenever you are looking at a safety point in a method question, there are 3 sections to it. So in this case, we've got the idea of a hot heater. Okay, so the idea here is that the heater is very hot and therefore it could actually cause burns. So there's the first 2 points. Identifying that you have a hot heater, it could cause burns. So how do you mitigate that? How do you avoid it? Well, you make sure that you are very, very careful. So take care when handling. Or in fact, don't touch this one. Now, again, you could take that from the point of view of the water. So you could identify that we have got hot water here that could cause burns, and therefore you need to be very, very careful when handling it, or you need to make sure you clean up spillages, those sorts of things. And one alternative risk you could go for here is the fact that you have an electrical heater and you've got water. So actually, another thing you can talk about is there is a risk of electrocution. Now, how do you avoid electrocution? Well, you don't want that electricity and that water to mix, so you make sure spillages are cleared up. So when tackling your 6 markers, remember EMMAs: equipment, method, measurements, analysis, and safety. So now we're asked to show the expected variation in temperature for the black and the silver bottle from the student's results. So we've got time along the bottom, temperature up the side. There's 2 marks available here. And so two things you need to look out for. The first thing is that because you're asked to talk about the black and the silver, there needs to be two lines, and both of these lines should be showing an increase in temperature with time. So your first thing to do is to have two lines. They won't start at 0 on the temperature axis. You won't get penalised if they do, but remember your water temperature isn't 0 at starting point. So you'll have two lines that start at the same point because we've said they should have the same temperature, okay? But we know that one of them is actually going to heat up at a greater rate. Now these lines could be a slight curve, they could be straight, it doesn't matter, but there needs to be two lines, and those two lines must both show an increase with time. You may even find that you have lines that then plateau out. So for example, you might decide that they do that, for example. It doesn't really matter. Two lines both showing an increase with time. The second mark is for knowing which of those is going to be black and which of those is going to be silver. So black surfaces are better absorbers of radiation, and therefore we would expect a faster or a greater temperature rise in a given time for the black surface. So our black surface will be our top line and our silver surface will be the bottom line. There's lots of variations you can have here in terms of what the lines look like. So both lines could reach the same temperature, but the silver one would reach it later. That would work. So there's lots of things you can do here, but the key things for the marks are two lines showing an increase in temperature with time, and of those two lines, the black line must always be higher in terms of temperature than the silver.